Hello, welcome to another electronics video, and this time I think it is high time that I look at a transistor. So I have a little one here. It's a 2222A, a 2N2222A, I think it's called. It's an NPN transistor. And I know that transistors are sort of like digital switches, and about all I know about them is that you give it voltage or current on the base, which is the middle pin, and then it allows current to flow between the other two pins. One's called a collector and one's an emitter, and you can use them as switches. Of course, from a digital circuit point of view, switching is probably the main purpose of it, but I think that they are also used to amplify, because like varying the voltage or the current on the center pin somehow affects how much current flows between the other two, so you can use a small current or voltage to make bigger changes, you know, in the other current. So that's how they like amplify things. That's, you know, the extent of my understanding there. But anyway, I found a small website of some simple, you know, like digital circuits to try putting together with transistors, and I thought I would try one of those out. There's actually a whole bunch of these. I've seen roughly the same circuit all over the web for like hooking up a single transistor and using it as a switch and then inverting it. So I thought the inverting is kind of cool because in one of my earlier videos I used an actual inverter IC, you know, one of these guys, to invert a button press so that the LED was on when you weren't pressing the button, and vice versa. So I thought it might be fun to actually just make an inverter out of an actual transistor, because it apparently is not very difficult to do that. So I'm going to hook that up and we'll see how that goes. So over here is this website I happened to find that had some pretty nice, you know, really like cleanly presented schematics for some simple circuits. There's a whole library of them, and I don't understand most of them. Well, I don't understand any of them really, but here we go. The first one was using an NPN transistor as a switch, and this one seems a little silly because, like, if you have a switch to turn the transistor on and off, why not just use the switch as the switch? But I'm going to do it and hook it up because it's very similar. There's just like a minor change to the circuit to then turn that switch into an inverted switch. So that's kind of why I figured I'd start here and then adjust it and go back. Now, this website has a whole, you know, like recommendations for how to hook it up on the breadboard. I'm going to kind of ignore that and try to just sort of follow the schematic and do it myself. I always forget how these switches hook up as to which way is which, but I'll start by putting a switch somewhere. I guess just anywhere here. I might end up having to rotate this switch 90 degrees because so far I think that's happened every time I've tried to use one of these push button switches. Okay, we'll hook up VCC to one side of the switch. VCC is positive. I'll hook it up there, and I'm going to move my switch so it lines up better. Okay, now I have VCC connected hopefully to one side of the switch. The other side they have going to a 10K resistor, which I have right here. And then that connects to the base of the transistor. So I guess I will just go over like this, and then the transistor is this way. Now, which one? The base is the middle, I know. I have the data sheet for this. I think this transistor, it's the right number anyway. And it says that the base is pin 2, which is the center, and this says it connects to the base, which is the center. Well, I already needed that. I knew that. I guess I didn't really need the data sheet for that. Oh, but which way is the collector and emitter? So this is going to connect on this side of the symbol, which is the collector. That's pin 1, and the flat side is facing towards me. So the collector will be on the left. Okay, so the collector of the transistor here also connects to VCC. That's easy, just a short little jumper there. Okay, and then the emitter connects through a 1K to ground, and then I'll put the ground here. Okay, So now I have this connection done, and then we have to tap it sort of in the middle here, so that connects directly to the emitter of the transistor, and it goes through a limiting resistor to the LED, which goes to ground. So let's see, I think I'll put the LED over here somewhere. The long one is the anode, and that's positive, so the short one's the ground. I think I'll just do this so that it's kind of over out of the way. Maybe I'll put it here, and then I'll run a line from here to here, which should connect, or no, I have to go through this. Well, I think I'm going to put the limiting resistor on the other side. I'm going to put that here. As far as I can tell, it doesn't matter which side it's on. There's probably some subtle difference, but I think the current on a series circuit is the same everywhere. So in theory, I think it shouldn't matter which side I put the resistor on. We'll see. Okay, now I just need this final connection. I think that's hooked up correctly. Now, if I understand this circuit correctly, all it really means is when I push the button, the LED will turn on, which of course I could have done in a far simpler way, but that's not the point. I mean, you know, you're not playing with a transistor if you just hook it up that way. Okay, that doesn't work. My theory would be, wait, I have to turn it on first. That would be helpful. No, it still doesn't work. Probably the switch is the wrong way. Or maybe the pin is bent. Nope, still not working. All right, well, that pin is bending. Let's take the switch out of the equation here and double check this circuit. I think I have, wait, hang on. This side is this is wrong. This is connected to ground and it should be connected to positive. So there's your problem. All right, let's do that. These switches do not fit very well in the breadboard. Let's see if I can bend this a bit. Whoops, and now we're off by 1 here. There we go. All right, it's hooked up now. I push the button and the LED turns on. So I think the way this is working is when the button's not pushed, there's no voltage or current going to the base of the transistor, and so therefore the connection between here and here is not connected. Essentially, it's disconnected, so it's open. And because that's open, there's no way for, you know, the positive current to get anywhere else, so of course nothing happens. Okay, so when I push the switch, the current can go through the switch, through this resistor, into the base. This is a 10K resistor, so it's kind of large. So I think it's probably, well, it's certainly reducing the current that's allowed to go into here. But because it makes a connection, it also allows a certain amount of voltage to appear here, where previously when I let go of the switch, there's no voltage. I'm curious as to why this doesn't have like a concept of a pull up or pull down resistor, actually. Why doesn't this need it? Maybe it does need it. But if it does, then why isn't it on the circuit? I've looked at a few of these, and they don't seem to ever have them, or they very rarely have them. So I actually did some searching around on the pull up, pull down thing, and this discussion here, which I had found earlier, there's quite a battle about this question. Yeah, I don't understand any of this. And there's a lot of people seemingly debating whether you need a pull down in this scenario or not. And oh my goodness, it just goes on and on. It feels like this must be the tabs versus spaces of electrical engineering, perhaps. I don't know. In any case, there's no pull down on this circuit, and it seems to work okay. But possibly there's some exception where there should be a pull down or a pull up on the base. I'm not sure. But in any case, getting off track here, the current when the switch is down goes here and it turns the base on, which allows the full amount of current to easily pass through here. And it goes straight to ground here, but it also goes through the LED. Now, I'm not certain why is this resistor even here? Wouldn't it just go straight down? Can we get rid of that one, actually? This resistor here. So if I take this out, then there's nothing there. Whoops. It still works. Okay, that I don't know why this circuit has this in there then. What is the point of that? It's almost like you're pulling this side of the LED down to ground, but why? I mean, it's connected to ground. I don't know. I don't know. If anyone knows, let me know in the comments. I have no idea why that's there. It seems to work without it. I mean, logically, intuitively, so to speak, I would think that you wouldn't need this because there's no connection here. And no connection means the LED is not going to light up until this establishes a connection by way of, you know, the switch here. Yeah, don't know why that's there. Okay, I'll just put it back for now. Still works. Okay, well, that's not very exciting. Push a button, get a light to turn on. I think what I'll do now is we'll move to the next one, which is the transistor inverter. It's the same basic design, and for some reason it still has this 1K in here, but now the idea is that the LED will be on, current will be allowed to flow through here until you push the button. And I'm guessing that works because when you push the button and the transistor turns on, it's now really easy to go to ground through the transistor as opposed to through this LED. So it would prefer to go this way. I guess in this case, a 1K here makes some amount of sense because if this wasn't here, you would have a short circuit through the transistor straight to ground, which I'm assuming would be bad. It seems like this is going to make the LED dimmer though, because there's now a 1K here. The only way for current to get to the LED is to come from, you know, positive through this resistor and then through its limiting resistor. So it seems like the LED would be a lot dimmer. I don't know, we'll see. So the main differences here are the base is still connected to the switch through the 10K. So there's no difference there, so I don't have to change that. The emitter, that's this side, now goes straight to ground. And we'll move this. Okay, so the emitter goes straight to ground, so I'll just move this up here. So the collector side now connects to VCC through a 10K, so that means I can just replace this, or through a 1K, with the 1K I had before, right there. And then we also tap off of the collector to go over to our resistor, or not the resistor, the LED. Okay, I think I have it hooked up. Let's see. Okay, it's on by default. That's the correct act. And when I push it, it turns off. Wait a second. No, that's right. That's exactly right. That's the inverted idea, that it's on when I'm not pushing it. It goes off when I am pushing it. So this works just like the other, the IC circuit from before, except it's just using a transistor. Now, as to understanding why it works this way, when this transistor is off, there's no connection between here and here, and so the current is going to go this way, which lights the LED. When the switch is on, it turns the transistor on, which allows current to go this way. So then the current goes through here and this way. Now, there's no reason it couldn't go this way too, but I'm assuming that because of that, you know, because this is more difficult, it goes this way instead. I think. I mean, there's the idea, the electricity goes, you know, in the path of least resistance, right? There's literally a resistor here, no resistor here, although I imagine the transistor has a little bit of resistance, and of course wires have a little bit of resistance. I don't know if that's the full explanation there or not. So that means that when I'm not pushing the button, the current's flowing continuously there. When I am pushing the button, current is just being wasted. It's still going, it's just being wasted. So, I mean, it must be moving, right? So I'm assuming that, you know, this is less efficient than a physical switch. A physical switch would literally break the connection, and of course there would be absolutely no current flowing. So this uses power even when it's off. Okay, so I don't know if I can tell, but I think the light is a bit dimmer. Now, what I'm wondering here is, why do this? Why have the resistor here and here? It seems like I could put the current limiting resistor, you know, at this spot and just get rid of this one. Of course, this is a smaller resistor though for the LED. That it's only the, I think I'm using the 220 here, and this one's 1K. So I guess that would mean that if I Well, let's just try it. This is the 1K one. So if I take that one out and put this one here, and then I'll have to connect the other side of the LED. Okay. Oh yeah, it's brighter. I don't know for sure if that comes across in the camera, but it's definitely brighter. So this is the brightness that I was seeing before. Oh, that's interesting. Now I push the button. It's not off. It's on still, just dimmer. Now why would that be? Why would that be? So this resistor no longer exists. I replaced it with a small one here. So when I'm not pushing the button down, this is off. So the current goes through like normal. When I push the button down, there's a 10K resistor here, which is supposed to turn the transistor on. Is it like not turned all the way on or something like that? It's like some of the current must be going both ways. Okay, I have no idea why that's... I mean, I know that at least my understanding is these transistors are not, they're not really digital devices. They, you know, the amount of current that passes through here is somehow proportional to what's going on the base. So I guess it might mean that with a 10K here, maybe it's not like fully on or something like that. And so that means that current can go this way really easily. And when I had the, when I had this resistor here and then this one in here, that was just enough resistance to make it easier to go through the transistor, or it maybe still went this way, but not enough to light the LED, or perhaps not enough to light it perceptibly. It's feeding 5 volts into that 10K resistor. That would resist a lot of current, but it also kind of like gives it a voltage. Nope, I gotta say, I'm not 100% sure why that's the case. Like, what if I wanted this LED to be as bright as it was before while going through the inverter? If I connected up the way this circuit had it originally, with the 1K over here, and then I put my current limiting resistor over here on this side, it's definitely dimmer. I don't know, this is 220. I could get close maybe with a couple of 100s. If I put a 100 here and a 100 here, so that'd be the equivalent of putting a 100 here and a 100 here, it seems like the sides would be kind of balanced, so it seems like current would go either way. Although in theory this should be easier, shouldn't it? But that might not be good enough. I don't know, we might as well try it, I guess. Okay, these are both 100 ohm. I didn't cut them down, so they're kind of tall and gangly. Now together they're 200, so that's pretty close to the 220 I had before, so it seems like the LED should be bright. Yeah, it's brighter. So if I push the button, it dims a tiny amount and barely at all. So I'm not really sure what's going on there for why when I turn this on, why doesn't it find it easier to go this way? Do I need a smaller resistor here? I don't know. Why not try it? I don't know the theory of any of this, so we'll give it a shot. I'll replace the 10K on the base here with, you know, a 1K and see what happens. Okay, ideally I would have a theory as to what would occur. This is smaller, so that means it's gonna allow more current into the base. Now I kind of thought transistors were voltage switched, but somewhere in, I think it was in the argument on this long thread, there was an argument about how NPN BJT, which is what this kind of transistor is, are current switched and not voltage switched, and I don't know exactly what the implications of that would mean, but maybe more current means more open? Okay. Maybe that was correct, because it's back to working with these smaller resistors in here. Huh. Okay. Well, that's kind of cool. I don't know if I don't know what the implications of that are, though. I mean, if this is a smaller resistor down here now, this is only 1K. Clearly it's letting more current through when I push the button. But where does that current go? I think it comes out the emitter, even from the base, I think. So if that's the case, I guess it just goes straight to ground, which means that when you're pushing the button, it's going to be consuming more current now. It's just sort of wasting it, sending it straight to ground. It must mean that the resistor, well, I don't know if it must mean this, but it feels like it means that when I push it, then the transistor is more on. And so this is a much easier path through. So it doesn't even maybe get over here and light the LED at all. Not perceivably anyway. Yeah, I don't know if that's what's going on or not. Well, I have no idea if I've discovered anything useful. I'm not quite sure how to make that fit in my brain as to what happened here. My primary interest is probably digital circuits, so I don't know how much more I'm going to hurt my brain trying to do these analog things. But like in digital circuits, I think they're a lot simpler because most of this is abstracted away, perhaps, in some fashion. It's mostly just about high and low signals and hooking them up to the right inputs. Well, I know there's points where the analog stuff collides with the digital, right? Like you need a clock source, for example. That's one of the things that I know I'm going to need if I can get to the point of hooking up this old processor, which is kind of the goal of this whole series. I will need some kind of a clock, and I gather that the clocks are kind of analog. Like you have to exploit how these transistors and stuff work, or use a crystal or somehow hook it up where you're transitioning from the analog world to the digital world. So I suppose you can't escape it entirely. Anyway, I guess that's it for now. Just exploring transistors. I don't know if it illuminated anything or not, but it illuminated this LED anyway, so that's nice. Unless you push a button. All right, if you like the video, thumbs up, subscribe. If you don't, do the opposite. And that's it for now. Thanks, bye.